Hi, hello, welcome to section 3 of chapter 7. In this section, we are going to learn about a topic called intermolecular forces. So let me define what is an intermolecular force is and come back to explain what is the significance of it. So intramolecular forces are the attractive forces between neighboring molecules. And these forces are also called as van der Waals forces, but they were primarily known as intermolecular forces. And sometimes we cut short it as IMF as a shortcut. We can also say it as IMF. So in chemistry, if you hear the word IMF, what is then IMF between these two molecules? They're trying to refer to intermolecular forces. So let's see, why do we need to learn this one, right? I got this slide to remind you where we started discussing about chemistry. We started discussing chemistry in chapter 1, right? And there I remember showing that slide where I told you that these are solids where they were highly packed one over another, and these are liquids and these are gases. And when I come to the liquids, I said like these molecules are not as highly as packed as solids. And when it comes to gases, I told you that those molecules are not really near each other, so that's why they don't have any shape. So that's why you cannot see them, right? That's what we discussed. Now, we did not discuss there what makes them stay in the form of solids, what makes them stay in the form of liquids, and why the gas molecules, we cannot see them, right? Let's discuss about that. So when we discussed about atoms in chapter 1 or chapter 2 or chapter 3, we said that atoms are the smallest form of matter, right? Really tiny, tiny matter. And it has really, really negligible mass and also negligible size, like, a millionth of a meter, the size of a molecule, typical molecule. So it's pretty difficult to see with the naked eye. So even if you think of a bunch of atoms, like really large molecule that is connected to each other, still that molecule is really, really small, even close to, 1 millionth of a size. So you couldn't, 1 millionth of a meter. So you cannot see such kind of small molecules. So what are we looking at? We are looking at molecules that were interacting with each other through one of the interactions as either ionic or intermolecular forces, okay? Because, again, because the atoms are really tiny, molecules, individual molecules made up by atoms are also really, really tiny. As a result, we cannot see them. So if you're seeing any matter with your naked eye, it is because there is an interaction between those molecules that is keeping them together. Intermolecular forces is one of that interaction. So one type of interaction that you guys learned in the previous chapter is ion-ion interactions, or in other words, electrostatic interactions between ions. So ions are literally positively charged and negatively charged. If you guys remember, I showed you sodium chloride lattice structure where the negatively charged chlorine were smacking the positively charged sodium, and they form a regular array of sodium and chlorine, sodium and chlorine. So we call that repeated structure as a lattice, and we call that as a solid structure. So ions can easily form solids because they have really strong electrostatic interactions between them. But covalent molecules do not have electrostatic interactions between them because, covalent molecules do not have ions in them. Covalent molecules at most have polar bonds, and some of them not even have polar bonds. So, but still you can see the polar molecules outside, right? You can see water, you can see cooking oil, you can see food, you can see trees that are made up of these non-metals. You can see a lot of things made by these non-metals, which means there must be some force that is holding these molecules together in large numbers so that they can acquire a meaningful shape that we can see it with the eyes. Those forces, those meaningful forces that are holding these molecules together are called intermolecular forces. The intermolecular forces are the reason why these non-metal containing compounds are acquiring the shape of either a solid or liquid. Obviously, gases cannot have a shape because gases are not having intermolecular forces, which is a huge proof that intermolecular forces are keeping molecules together. You cannot see gases because they were not near each other, so that they do not have intermolecular forces between them to keep them each other because they fly away. So they do not have shape. Whereas opposite to gases, solid and liquid has intermolecular forces between them. As a result, they were acquiring the shape. And in this lecture, we are going to study what type of intermolecular forces out there. There are a total of 4 different of them, and we are going to go one after another. But this is the introduction that you really need to hear. And I'm going to summarize again. Intermolecular forces are the attractive forces that exist between 2 neighboring molecules. I'm going to tell you what type of attractive forces there are, each by list when I discuss each one of the 4 intermolecular forces. But for now, you can see the uses of intermolecular forces, which is helping the molecule to have its physical form of the shape of solid or liquid. As a result, they will have, let's say, different chemical and physical properties. Again, going back to water, which is the life-giving liquid to us, the water is boiling at 100 degrees Celsius because it has intermolecular forces that hold each water molecule together not to leave the clump of liquid water molecules. Each of the rest of the water molecules are holding the water molecules not to turn into gas until 100 degrees Celsius, which is a huge gift to us because think of how hot it gets in summer. If the water has a low boiling point, all the water in the lakes will be gone to the air and we have no water to left with and we will die with the thirstiness, right? So it's a gift. It's a gift from nature that it created water that help us where it doesn't boil out less than 100 degrees Celsius, which is really hard to get. But the only reason it doesn't boil out is because of the intermolecular forces exist between them. That's why I'm getting excited to show you the type of intermolecular forces between these molecules. The first one is called dispersion forces, also called as London dispersion forces. They both mean the same thing, 2 different names for it. In short, it is called dispersion forces. So the dispersion forces are the weakest form of intermolecular force. We have 3 main intermolecular forces and one will the ions. We don't really worry about ion type intermolecular force. So these 3 intermolecular forces, I'm going to label them as weak, moderate, and the strongest intermolecular forces. We are going from weak to moderate to strongest intermolecular force. And in here, we are discussing the dispersion force, which is a weak intermolecular force. What it means is the interaction with one molecule to another is weak. Let's see why. Dispersion forces result from the Coulombic attractions between instantaneous dipoles of molecules. Okay, and here I added the word especially all molecules because this instantaneous dipole can happen in any type of molecule. Excuse me. All types of molecule is the keyword. Okay. So if you look at a molecule, you automatically think that it ought to have dispersion forces because it is an instantaneous dipole. I'm going to show you what is instantaneous dipole means. It is the dipole that created as a result of movement of electrons. Okay. Let me try to explain that again. It's it can get tricky because there is no polarity there. So especially it is important, the London dispersion forces are especially important in nonpolar molecules because London dispersion forces are the only forces experienced by the nonpolar molecules. Nonpolar molecules with no polar bonds has no polarity in them, so they cannot have these positive and negative dipoles which attract another molecule positive and negative dipole, and to have interactions between them to keep them stable by warming one over another. But if you have a nonpolar molecule with no polar bonds, the only type of interaction they can experience is dispersion force. Let's see how do they do that, right? I got a couple images here to help with your imagination because it's somehow little bit hard for students to imagine. I don't blame them because it definitely looks a little bit tricky. Look at this example of helium. Helium is a noble gas, right? I specifically choose noble gases because if it works on noble gases, it ought to work on any other element, right? Noble gases are inert. They don't like to interact, but here they were interacting because dispersion forces work on any type of atom or molecule, be it nonpolar or polar, okay? But here we are mainly going to focus on nonpolar because it's the only force they get to have. So let's have their focus here, okay? Let's put them on limelight. That's what I was going to say. So you have a helium here. Let me get my laser pointer. You have a helium here with the 2 protons in nucleus and 2 electrons revolving around. You have a helium here with the 2 electrons revolving around. So when you have electrons revolving around any nucleus, they were continuously moving, right? According to Heisenberg principle that we discussed in chapter 3, they move at the speed of the light. They continuously move and move and move. When they continuously move, there is obviously at one stage, there are no electron clouds and there are electron clouds on another side. So let me repeat that. When the electrons are moving around the nucleus, there is a movement, even if it is the slightest, smallest, tiniest fraction of second movement, there is a movement where electron clouds shift one side and electron cloud is not present on another side. So when these electron clouds temporarily shifts on one side heavily, it creates a instantaneous temporary polarity. Okay, that is what we mean by saying instantaneous dipole here. What is an instantaneous dipole is when these electrons continuously moving around the nucleus, temporarily within a fraction of a second, they just move on one side, which they always do. When they move on one side, the electron cloud creates the temporary negative charge on that side, even if it is really fraction of a second. That is attracted towards the opposite element, nucleus. Your nucleus contains positive charge and it would like to experience that extra electron cloud. So the nucleus of one helium atom here is attracting the instantaneous dipole created by another helium element, because when electrons are one side heavily, it does create the instantaneous dipole. So instantaneous dipoles will attract the positive end of one element with the negative end of one element. That is when you observe the dispersion forces. I got one more GIF image here to show you the same concept. Here again, another noble gas, neon. You see, neon electrons are revolving around continuously, but at some fraction of the second, one neon electron cloud is temporarily on one side heavily, and another neon also having the electron cloud temporarily away, exposed its neon center with a positive charge to other neon with the negative end. That creates temporary dipole, instantaneous dipole, which is not permanent because there is no polarity in them. That's why we are calling this one as instantaneous. Because it is so instantaneous, we are calling this one as a weak intermolecular forces. Okay. Here are some examples of how they interact. Basically molecule is nonpolar. It doesn't really have any polarity in them. So electron cloud fairly stays in the middle, right? It doesn't have to move anywhere. But because of this electron cloud continuously moving all over the molecules at a fraction of a second, again, one side is electron heavy, one side is electron less. So the electron heavy side will reach out to the electron less side molecule. As a result, instantaneously they create dipole. As a result, they have these interaction between them. Okay. So as a result, we observe these London dispersion forces. Again, this is another example of doing the same thing. Electrons are continuously moving. As a result, they are creating these partial instantaneous positive and negative dipoles. So negative dipole is attracting the another molecule positive dipole. As a result, they were all staying near each other. Now, it is very important for molecules to stay near each other to have this stability. Even though, molecule, once the atoms form molecules, atoms achieve stability. But what about molecules? Molecule alone is not just stable enough. By having the stability for a molecule means by not easily getting evaporated, even at low temperature, by not getting frozen easily. So by having stability means to stay strong, to not to get evaporated is the good example. So I'm just repeating it. So again, coming back to water, easy to say. Water, if it not has these intermolecular forces between them, it would have in gas all the time. Because it has these intermolecular forces, it is predominantly found in liquid form at room temperature. Okay, these are intermolecular forces. Again, one thing if I have to highlight is, let's see, let me get red color. No. This one. The dispersion forces are mainly observed in nonpolar molecules with no polar bond because it is the only intermolecular force they experience. Again, it is also found in other polar molecules, but it is going to be negligible for them because it is a weak intermolecular force, but it is the only force that is experienced by nonpolar molecules with no polar bonds. Okay. And here we are going to discuss the types of intermolecular force, how to differentiate the strength of the London dispersion force from one molecule to another. Right? You now know that okay, nonpolar molecules experience the London dispersion forces. But what if there are two different nonpolar molecules that are different from each other? How do you use these London dispersion forces to predict these physical properties such as boiling point or melting point? So here are the guidelines, and there are only two things that you need to look for. The greater the mass, in general, the greater the London dispersion forces experienced by both of the molecules. As a result, the larger mass containing molecules will experience greater physical properties, let's say higher boiling point. And also, let's say in the cases of when mass is same, you can look for the surface area. The surface area, I have examples to show you what I mean. I'm just going over these details. So what is a surface area means is the molecule smaller or larger. Smaller molecule will have smaller opportunity to experience those instantaneous dipoles, but larger molecules has many opportunities to experience those instantaneous dipoles for over a long surface area. So higher the surface area and higher the physical properties such as boiling point that you can expect. So here is a beautiful set of examples that we are going to look and see. So from these molecules on the left, methane to butane to hexane to octane, all of these are nonpolar compounds because all of them has either carbon-carbon or carbon-hydrogen bonds. As a result, the only intermolecular forces they can experience is London dispersion forces. Okay. Now, that's common, right? So London dispersion forces, but they were different from each other. They were different in sizes, which means they were different in masses, and they do have different in surface area. Let's see just by using the mass theory that if you could differentiate the physical properties of one molecule to another. Methane only contains one carbon, whereas butane contains 4 carbons. See the difference in the boiling point. The methane has a boiling point of negative 164 degrees Celsius, whereas the butane has 0 degrees Celsius. The huge difference. What is the difference between these two is one is bigger, so larger, so butane has a greater scope for higher London dispersion forces between them. So more butane molecules are overlapping with more butane molecules. As a result, they were not easily getting evaporated at lower temperature like butane. Let's compare butane with a molecule that contains 2 more carbons than butane, which is hexane. The boiling point jumped from 0 degrees Celsius to 68 degrees Celsius. See the huge difference there. What's the only difference between them is one is a little bit more larger because of 2 extra carbons, so mass is bigger, so does surface area increase as a result of greater surface area in hexane. Again, more hexane molecules are overlapping efficiently over another hexane molecule with the help of instantaneous dipoles created by each one of these carbon centers and hydrogen centers. As a result, hexane molecule is relatively more stable compared to butane. If it is boiling at 68 degrees Celsius, which means it is a liquid at room temperature, whereas butane is not a liquid at room temperature. Now let's compare hexane to octane. Octane is one of the main components present in a gasoline that we use, has 2 more carbons than hexane, but it has the boiling point of whooping 128 degrees Celsius. See the again huge jump. Again, what's the only difference? Bigger in mass, larger in surface area. As a result, much more scope for more instantaneous dipoles between each molecule to another molecule. As a result, they were packed really nicely one over another. As a result, they were not getting evaporated. So it is hard to take away octane molecule away from the bunch of octane molecules because they have the greater intermolecular forces between them compared to hexane, where it is in a bunch of hexane molecules. So similarly, you can, as you go down, you can see that. Now I have a comparative molecules, but with a ball and stick model to observe the surface area phenomena as well. So first set is mainly discussing about the effect of increasing mass on a boiling point. So methane to ethane to propane to butane, where the boiling point is increasing because mass is increasing from here to here to here. What if the both molecules have same mass? How do you decide which one is going to have higher boiling point, which one is going to have lower boiling point? Is in those cases you refer to the surface area if the molecule has the same mass. In here, both the molecules has the same number of carbons, both the 2,2-dimethyl propane and N-pentane, both has 5 carbons and 12 hydrogens. So as a result, mass is same. So because of that, you're going to check the loose structure of it and check which one has larger surface area. So in 2,2-dimethyl propane, molecule is shorter, it's packed, the more carbons are connected to central carbon, whereas in pentane, 5 carbons are connected to each other in a linear fashion, so it is a longer molecule. So N-pentane has a larger surface area compared to 2,2-dimethyl propane. That's why you can see this huge difference in electronegativity. One is only 9.5 degrees Celsius, another one is about 36 degrees Celsius. Okay. Hope you got the London dispersion forces already, but if not, I got some more examples here to rediscuss. Again, to review what we just did. We are discussing about intermolecular forces. We said intermolecular forces are the attractive forces between neighboring molecules. What is the use of intermolecular force is it helps keep the molecules together so that they will have the stability in a pack of molecules. So sometimes they acquire a solid shape, sometimes they acquire a liquid shape. Gases do not have intermolecular forces between them. As a result, they were gases, single molecules. So one type of intermolecular force that we are currently discussing is dispersion forces. And dispersion force is created by the instantaneous dipole created by the movement of electrons in a nonpolar molecules. Okay, and we discuss how to differentiate the physical properties of one molecule to another based on mass and size of it. Let's see if you can do the same here in these examples. Here you have a comparative examples from same group, fluorine to chlorine to bromine to iodine. Same group, but from different periods, which means they have different masses, right? 38 to 70 to 160 to 253. So what we just discussed is mass is a good indicator in predicting the London dispersion forces, because most of the times it is related to surface area as well. So smaller the mass, lower the boiling point, and bigger the mass, and so is larger the boiling point. As the mass increasing, boiling point is increasing. So by iodine with the 253 mass, you have the boiling point of 184. See, the boiling point is increasing as the mass is increasing. Also, you can see the effect in the physical states of it. You know, F2 and Cl2 are almost gases because the intermolecular forces provided by these intermolecular forces between these fluorine and chlorine is not sufficient enough to even keep them as in either liquid form or solid form, because it's a tiny surface area and they can, you know, barely interact one with another. That's why they are still gases. But Br2 is liquid, but iodine is solid. See, only difference between them is mass and the larger surface area. By iodine, it is solid, but Ft is a gas. So if someone asks you why chlorine is a gas and iodine is a solid, now you know how to explain. You will explain them that there are intermolecular forces that play a major role in determining the physical property or physical state of a molecule. Because Cl2 is a smaller molecule, it has a smaller surface area, so does the smaller dispersion forces. That is not enough to keep them as in solid shape, whereas iodine is a bigger molecule with lots of shells, so larger radius between the two iodines. As a result, a great instantaneous dipoles experienced by bunch of iodine molecules over another. As a result, it is solid. Fantastic explanation. What's wrong with it, right? All right, so far we're done with the first intermolecular forces. Now we are going to go over the second one. Hopefully it gets a little bit faster. So, but this topic requires to go over again and again and again, because over the years I have seen students revisiting these topics, asking me to re-explain why. So, which is, you know, I'm okay to explain all this time, but what it makes me think about is maybe I need to explain more thoroughly, many times, review it, even in my first attempt, so that they wouldn't have this confusion when they were trying it the first time. So, but even after this, if you still have questions, you can happily contact me. I will happily go over this. That I'm just saying, the reason I'm taking my time in explaining all of these topics, because these topics need to be explained in such a way. They were complex topics. So dipole interactions. This is the second type of intermolecular force that we are going to discuss between nonpolar molecules, between non-metals. So this is a medium intermolecular force, a moderate intermolecular force. So which type of molecules experience this moderate intermolecular force is the polar molecules. And here we highlighted that dipole interactions are the attractive forces that act between polar molecules. Excuse me. Only polar molecules will experience dipole-dipole interactions. Non-polar molecules cannot have dipole-dipole interactions, because having the polarity is the primary requirement. So what is a polar molecule is, polar molecules have polar bonds with atoms that have a significant electronegativity difference between them, namely at least 0.5 electronegativity difference, which causes the more electronegative atom to have a negative dipole, partial negative dipole, and the less electronegative atom to have a partial positive dipole. So when you create these partial negative and partial positive dipoles, the opposite dipoles of two molecules attract with each other from every angle possible, from top to bottom or side to side. As a result, they interact with one another through intermolecular forces, which is what we are discussing. How one molecule interact with another molecule to keep whole molecules physical properties larger. So here we're discussing the attractive forces, and here we're discussing which forces that doesn't work. You cannot ask two negative ends and two positive ends to attract with each other because they would have same charges and they would just repel with each other. And here just you're looking at the same thing in a different perspective. So in a molecule, you have a combination of both positive negative combination, which is attractive, and sometimes a non-attractive combination of positive positive and negative negative, which is not useful. But nevertheless, the dipole-dipole interactions are relatively stronger than the dispersion forces, but still it is a moderate intermolecular force. You will understand why it is moderate when we discuss the last intermolecular force. So it does again help create the solid or liquid form for the non-metal compounds by having the positive and negative, positive and negative, positive and negative interactions. Doesn't matter if it's solid or not, but the main reason in the first place the molecules are looking like a solids or liquids is because they have intermolecular forces in the first place. Okay, it depends on the type of interactions they have and the size of molecules they have to be called as a molecule as a solid or liquid. But here we're just focusing on how having intermolecular force in a molecule is going to change its physical properties. Okay, here is an example where you can compare the physical properties of one molecule with another molecule just by observing the intermolecular forces present in those molecules. Okay, let's look at the first molecules. So the first molecules that you have here is propane molecule, and clearly that molecule is a nonpolar molecule. As a result, only type of intermolecular forces it can experience is London dispersion forces. So that molecule with the London dispersion forces, also again here you can see the dipole moment. It's tiny. 0.1 is really tiny, low dipole moment. As a result, it has low boiling point. Let's compare with another molecule that looks very similar in size, right? With first molecule has 3 carbons and second molecule dimethyl ether has 3 atoms. A carbon is replaced with oxygen. So now this molecule has a polar bond because oxygen carbon bond is a polar bond. So the interactions they can have is both the London dispersion forces, you can say London dispersion forces as a default for any molecule, but also mainly dipole-dipole interactions. As a result, here you can see the dipole moment for dimethyl ether is larger. As a result, its boiling point is also greater for dimethyl ether. For methyl chloride, the next molecule, this molecule, if it is small, it has larger dipole moment. As a result, it has bigger dipole moment as well. And next molecule, acetaldehyde, has also dipole moment as its intermolecular force. And also, London dispersion forces default, you can say. And also it has a larger dipole moment. As a result, it has a bigger boiling point. And so does the estronitrile. It has polar bonds, so larger dipole moment. Here you can see it with the boiling point change as a huge change. The only reason it has that huge boiling point, even though it is small molecule, because it has a strong dipole-dipole interactions with another molecule, which is holding this molecule stable all throughout the CH3CN combination of molecules. So what it does is it keeps one CH3CN interacting with another CH3CN, like two magnets are close to each other. The stronger the magnetism, how strong it is to, how hard it is to pull one away from each other. So think of as magnets. These are CH3CN is like two magnets that are stuck to each other really strong. As a result, it's really hard to separate them. So you need to apply lots of energy. That's why its boiling point is 82 degrees Celsius. What does boiling point tells us is when the liquid converts into gas, where gas molecule experience no intermolecular forces, so it is on its own. So to take it to that stage of breaking those intermolecular forces, acetonitrile requires lots of heat, which means lots of energy, which means it has really strong intermolecular forces between them. So dipole-dipole interactions are moderately strong intermolecular forces. Now comes the last intermolecular forces, the hydrogen bonding. It's also the strongest intermolecular force. The hydrogen bonding is a special type of intermolecular force. Remember the word, a special type of dipole-dipole interactions. We are calling it special because it is rarely seen and only seen when these below conditions met. The conditions are that the hydrogen must be present in, let me get a highlighter and highlight that. The hydrogen must be present in, oh, sorry, it's not working. So the hydrogen must be present in or connected to one of these three atoms, nitrogen, oxygen, or fluorine. I cannot say how many times let me repeat that. I cannot stress enough how important for you to remember that. To observe the hydrogen bonding in a molecule, you have to clearly see a Lewis structure in that Lewis structure. You have to clearly check for if the hydrogen is directly connected to one of these following elements. If not, you just have dipole-dipole interactions. But if you happen to have hydrogen on, again, hydrogen directly on nitrogen, or hydrogen directly on oxygen, or hydrogen directly on fluorine, then only you have hydrogen bonding. Otherwise, it will be just a simple dipole-dipole interaction. So why hydrogen bonding is special is because the combination of hydrogen on fluorine, oxygen, and nitrogen creates one of the largest electronegativity differences in non-metal bonds. As a result, the bond is extremely polar. It is, if you remember the ionic character, it's high in ionic character. As a result, one negative end of a molecule will attract the another positive end of the molecule really, really strong. As a result, it almost creates a semi-bond. And you write it like that. You write the hydrogen bond like that. And that is almost a semi-bond. That's strong it is. And we call that in chemistry as a hydrogen bond. It is just another way of looking at things. Again, hydrogen bond is a type of dipole-dipole interactions and only seen when hydrogen is directly connected to nitrogen or oxygen or fluorine. Why it is because is when hydrogen is connected to only one of these three atoms, the electronegativity difference between these two bonds, these two atoms in a bond is really large. As a result, the electronegativity of nitrogen and oxygen and fluorine will take the electron cloud away from the hydrogen in that bond. As a result, it creates a huge negative charge on one side, huge positive charge on another side. So these negative and positively charged particles will attract each other towards each other strongly. As a result, it almost creates a semi-bond, which we call as hydrogen bond in chemistry. Hydrogen bond is the strongest intermolecular force, and I'm going to show you the data, how strong it is in the next slide. Okay, so before I move on, pinch yourself if you have to, because for some reason it doesn't stick with some students. To observe hydrogen bond, you need to clearly see hydrogen connecting to nitrogen, oxygen, or fluorine directly. If not, you don't have hydrogen bonding. You're just bluffing. All right. Let's see why hydrogen bonding is really strongest in comparison to another type of intermolecular forces experienced by other molecules. Here in this list, you can see all group 6A elements in red color at the top. Follow the laser, right? And 7A, 5A, and 4A, right? Compared to all of them are connected to hydrogens. You can see the water is really high in the list. Water has 2 hydrogen bonds and it has a boiling point of 100 degrees Celsius. And all other elements from the same group, even though they have similar connection like H2S and H2SE and H2Cl, see how hugely the boiling point drop between H2O and H2S. There is almost like a 150 degrees difference between H2O and H2S. It is because H2O has hydrogen bonding, H2S does not have hydrogen bonding. Only difference is H2S is experiencing just dipole-dipole interactions, but H2O is experiencing dipole-dipole and hydrogen bonding interactions. So let's look at the list again. HF has about, like, say, 20 degrees Celsius of boiling point, whereas HCl has about negative 80 degrees Celsius. Again, almost like 100 degrees Celsius difference between HCl and HF. The only difference, HF has hydrogen bonding, HCl only has dipole-dipole interactions. Let's look at NH3 versus PH3. NH3 has, let's say, negative 40 degrees Celsius boiling point, whereas PH3 has negative 10. Again, like negative 60 degrees Celsius difference between these two molecules. What's the only difference? NH3 has hydrogen bonding, PH3 does not have hydrogen bonding. Let's look at the first element from period 2 in comparison to H2O, HF, and NH3. CH4 has about negative 160 boiling point, which is the lowest of H2O, HF, and NH3. Again, what's the difference between CH4 and rest of the 3 molecules that are sitting on the top of this list is CH4 does not have hydrogen bonding, does not have dipole-dipole interactions. It only has the just dispersion forces. So do you see the effect of intermolecular forces and different strengths of intermolecular forces that we discussed and its effect here in just one slide? This is why I said for the comparable size molecules, London dispersion forces are the weakest compared to the dipole-dipole, but dipole-dipole is a moderate interaction compared to hydrogen bonding. This is the priority order. The molecule has hydrogen bonding, it will show greatest the boiling point compared to similar sized molecules containing dipole-dipole and just the dispersion forces. So hydrogen bonding is so special, right? Because it is having high boiling point, and most notably, it is keeping water as a liquid for us to survive and live. In addition to in addition to the advantages of keeping water as a liquid at that temperature, hydrogen bonding is also helping us to survive by helping us creating the proteins in a shape that it ought to be. Here you're seeing an example of protein folding with the help of hydrogen bonding. Now, protein is an amino acid structure. Well, I guess this is when all the biochemistry, I guess this is when I get the attention of biology, biochemistry, and anatomy physiology students, because I'm discussing about proteins. Now, in the proteins, you have amino acids, like you guys know, or many guys that are from biological sciences. It contains, sometimes it contains hydrogens and nitrogen, or OH bonds, or COOH, depending on what type of amino acid you have. And those hydrogens can interact with another molecule, oxygen or nitrogen, like you see here. As a result, they form folding structures or colloidal structures, we call. As a result, they form these, secondary structure, tertiary structure, or quaternary structures. And, all these enzymes that you're thinking about, these enzymes are basically a folded structures of proteins in a different shapes, and they fold differently because of the intermolecular forces. Some use just the dispersion forces, some use some use dipole-dipole, and some use hydrogen bonding. And here's an example of a molecule of a life that I call it is a DNA molecule that you're looking on the right. Very popular, right? Helical structure. This helical structure is possible because the hydrogen bonding between one strand of DNA with the another strand of DNA. Otherwise, there is no chemical bond between them. DNA is basically two different strands, two different protein chains, with obviously other molecules in it. So those molecules will attracted to each other to form these colloidal structure or the helical structures with the help of the hydrogen bonding that they were going to form between these structures. Except that, unless we have these hydrogen bonding intermolecular force, there wouldn't be life, as you can see. Now you can see how important the intermolecular forces are, because it is helping us to create or keep the DNA stable and helping us to reproduce by giving the DNA in the helical form to our efforts to reproduce in all of this. Very cool, very cool. I love hydrogen bonding. I love everything it does to us. All right, let's work on a practice problem and wrap this lecture. What kind of intermolecular forces exist in CCl4, CH3COOH, and CH3COCH3 and H2S? All right. For this, first of all, to predict the intermolecular forces of any molecule that you are asked to, unless you are given a Lewis structure, you cannot work on it. So you have to draw Lewis structure by yourself now for each one of these molecules, and you have to be really good at drawing those structures because your answer is depending on how correctly you draw the Lewis structure. So first, try correctly draw Lewis structure by pausing this video, then look at the answers. Draw Lewis structures and look for polar bonds or nonpolar molecules or polar bonds with hydrogen bonding. Then you can correctly comment on what type of intermolecular forces are there. So that's what we discuss here in the strategy. So your CCl4 structure should look like this, and your CH3COOH structure should look like this, and your CH3COCH3 structure should look like this, and H2S structure should look like this. Now, only half the job is done. You just have the starting material structures. Now your job is to identify the intermolecular forces present in each one of them by identifying the molecule as a nonpolar or a polar with the dipole-dipole interactions, or a polar with the hydrogen bonding. Okay, first molecule is a nonpolar molecule, so it just have London dispersion forces only. Second molecule is a polar molecule because I see polar bonds CO and CO, and they were not canceling each other. As a result, it is a polar molecule. But do you see hydrogen bond? I see hydrogen bond. I see hydrogen bond here because I can clearly point out. Excuse me. Let me get different highlighter color. I could. Oh, let me erase that first. I could clear. Oh, sorry again. I thought I changed the color. Apparently, I did not. All right. Eraser again. Ink highlighter. Now I get it. What's going on? I clearly see hydrogen bonding because hydrogen directly connected to oxygen. So this molecule has hydrogen bonding. Yes, it has dipole-dipole, but also most importantly, it has hydrogen bonding. Next molecule has a polar bond because there is a CO bond, but I do not see any hydrogen bonding in it because hydrogen is not directly connected to it. So it just has dipole-dipole interactions. And the following molecule, H2S, has a polar bond in it, but I don't see any hydrogen bonding because there is no nitrogen, oxygen, or fluorine. So it just has a dipole-dipole interactions and dispersion forces. That is how you would answer. Like, I'm going to give you a bunch of problems to you in the test or any test that you take in chemistry. People expect you to predict what type of intermolecular forces that you think they have in that particular molecular structure. Okay. Let's see. The last slide that I have here is about one of the least known intermolecular force, but it's no biggie. The previous three we discussed are the most important intermolecular forces because this is kind of mix and match intermolecular force between covalent and ionic molecules. So this molecule interaction is called ion-dipole interactions, where it occurs between a ion and a polar covalent molecule. So as you can see, ion has a positive charge, and a polar covalent molecule obviously has a partial positive and partial negative charge. Obviously, partial negative side of the polar molecule will attract the positive side of the metal. As a result, they form these intermolecular forces. It's very easy to observe, and it usually occurs in solutions. Well, you can think of it, it is the reason why solids will dissolve in water. Like why NaCl dissolves in water is because sodium can form these intermolecular forces with water. Unless sodium can form these intermolecular forces, it would not have dissolved. So here you see sodium surrounded by water molecules when you dissolve it. These are called ion-dipole attractions. That's all from this part. I know this is long chapter, and each chapters are long, each sections are long, but they were highly important topics, and I don't want you to miss out on opportunity on nailing the understanding of these topics. I hope you nailed the understanding of these topics and got everything you need to understand this topic. I will see you in the next section of this chapter.